This is the 2010 Waves paper for Level 2 Physics, and we're up to question 4. And this is the Physics Lounge, just in case he didn't know where you were. Henry listens to music on his radio while driving. There are two radio stations that he usually tunes to. Radio station A broadcasts on its FM network using radio wave 93.4 MHz. So that tells us the frequency of the wave. This will be frequency A, since we've also got a B down below. Radio station B, which broadcasts on its AM network using a radio wave of 856 kHz. So that's the frequency for B. Calculate the wavelength of the radio wave used by radio station A. Okay, now it may seem like we've got something missing here. We have the frequency, so we've got the frequency. In this case, for radio station A, it's 93.4 MHz, or 93.4 times 10 to the 6 Hertz, as it says up here. So we've got the frequency, and we're asked to find the wavelength, but it seems like we're missing the speed. So what is the velocity of this wave? Can we work it out anywhere? The answer is yes, we can work it out. These waves that are travelling, even though we don't think of them as light, because light we usually think of as visible light, they're non-visible light, they're radio waves, electromagnetic radiation. They're still light, they're just of a frequency or wavelength that we can't visibly see. We can detect using our FM radio. Anyway, so the speed of light is 3.00 times 10 to the 8 meters per second. And you can check that on your resources on your particular exams, but I'm pretty sure that's what the one is they used here. So then we use our formula V equals F lambda, and we're trying to find lambda, so we're going to rearrange for that, which means lambda equals V over F. Now it's just a matter of plugging in your numbers. V 3.00 times 10 to the 8 meters per second divided by 93.4 times 10 to the 6 Hertz. And then your final answer, I'm not going to plug the numbers in and calculate, I'm just going to tell you what it is. Final answer is 3.21, and there's a wavelength, so that's meters, it's a distance measurement. Okay, and we've done that to 3 significant figures, because the speed of light is given in the resource to 3 significant figures, and our frequency is given in 3 significant figures. So when multiplying and dividing, we use the least number of significant figures. In this case they're both 3, so that's what we will use. B. While driving on hilly terrain, Henry notices that he can only tune into one of these 2 radio stations. Explain why he can hear music from only one of these 2 radio stations. In your answer, identify which radio station he can hear, giving reasons for your answer. You may use calculations and diagrams to justify your reasoning. Okay, the picture's, whoops, I didn't mean to do that. The picture is irrelevant. In fact, I'll change the colour, there we go, brightened up a bit. The picture's irrelevant. This concept we need to identify first before we can move on, because it's going to be a bit too difficult just to jump straight into the answer, and this is an excellence question. If you have access to the marking schedule, you can see that. I thoroughly recommend getting the marking schedule and going through these papers with them. Anyway, carrying on. This is the concept we're looking for here is diffraction. Diffraction, and one of the common questions or understandings that we have with diffraction. Well, first, what is diffraction? Diffraction is waves bending around barriers or spreading out, coming through gaps, like interference, which is a later part of this question. So one of the key considerations is the wavelength of the waves will affect the diffraction. So the closer the wavelength is to the size of the gap, if it's dealing with a gap, then the more diffraction you will get. And in the case of these radio waves, longer radio waves will be able to diffract over the hills better. So that's actually going to form part of our answer. So long wavelengths diffract better. So you can hear a longer wavelength further away. And it suggests we use calculations. You may use calculations or diagrams to justify your reasoning. So what we need to do is work out which of the 2 radio stations has the longest wavelength. And there's two ways we could do it. We could actually perform the calculations, or we could just look at our v equals f lambda equation, because the velocity is the same for both of them, so there's no impact there. But the one with the longest or the highest wavelength will be the one with the lowest frequency. So if we go up and have a look, we can see we've got 93.4 megahertz, that's 93.4 million hertz. We've got 856,000 hertz. So this is the lower frequency, which will mean it will have the higher wavelength. And so radio station B is our answer. Radio B can be heard. Okay, and the explanation, as we say, is the longer wavelength, which will diffract better. This is more of a way of explaining it from a teacher's perspective, so it's probably a good idea to do the calculation, and you can find that the wavelength of that radio station B, when you put in the velocity 3 times 10 to the 8 divided by the frequency 856 kilohertz, I think 856,000, anyway, you end up with about 350 meters. That's a much larger wavelength than the 3.21 meters we found above. Okay, so in your answer you need to identify which one has the longer wavelength. You need to say that longer wavelengths will diffract more or better. Better is a little bit of a vague term, more is probably better. Ha. And then you can say therefore radio station B is the one which will be heard. Yeah, moving on. Ashley shines a red laser through 2 slits. He obtains a pattern on a screen as shown below. And this is your classic 2-point source interference. We've got point source 1 and point source 2, and they're point sources because they're radiating out evenly in all directions from both of these sources. Okay, so see, describe what would happen to the pattern if the screen was brought closer to the barrier. Alright, this is a very good one. There's a number of things that could happen. This is an achieved question, so I need to point out one, but I'll point out several things. If you remember, these things are radiating out, so there's kind of this square or the square factor that's playing into it, where the further out you go, the more the wavelength disperses. So what was smaller here, as it spreads out, it'll disperse over a large, so the energy of the wave is going to disperse, or we might say the intensity of the wave is going to disperse more. So that's going to result in the further away it is, or the screen's coming closer, so it would result in bright fringes. So the bright parts will be brighter. That would also result in probably less fringes being shone, because as you can see, as you move closer, you might lose some of these ones out the side that are heading way off over here, and this likewise heading way off over here. So as the screen comes closer, you get less and less of these fringes appearing. So the fringes will be brighter. You'll have less fringes. And when I'm saying fringes here, I'm referring to the bright fringes. You could also talk about the dark fringes. And what else? Oh, the other obvious thing which relates to that is the fringes will be closer together, because the distance of spacing is obviously decreasing. So I won't write that one down, but that's part of it too. D, explain why every alternate band is a dark band. Ooh, this is a goodie. So we're explaining why every alternate band is a dark band, and this is an excellence question as well. Where do you start? So the dark bands are points where the two waves are interacting and adding and cancelling out. So we would call that destructive interference. Destructive interference. That's my short for interference. And we would call these nodal lines. Just to throw in a bit of terminology, because examiners like that, and it's also good to know what different people talk about. And the idea here is that their two waves are 180 degrees out of phase, so they're exactly out of phase when they meet. So we have a crest meeting when adding to a trough at the dark fringes. And this happens when, this is sort of linking in with that 180 degrees out of phase, when we have we're half a wavelength path difference, or three halves, or five halves. So it has to be an odd number of half wavelengths out. Okay, and the other side of this is explaining where the constructive interference comes from, because you can't have dark fringes if the whole thing's dark. So you have to explain where the constructive part comes from, which is exactly the opposite for these there. If we were to rewrite parts of this, they're anti-nodal lines, it's constructive interference, it's 0 degrees out of phase, or we could just write that's in phase. And it's a crest plus a crest, or a trough plus trough. And we would talk about a whole number of wavelength path difference. Okay, if you're not sure about the path difference stuff, go check out the videos that I've done previously explaining the concepts. But this one's getting long. Thank you for listening.